So the purpose of this talk is to tell you a little bit about the tech components of an educational ecosystem that I've been developing called Bricklayer. And so here's an outline of what I intend to cover. So first, I'll give you an overview of Bricklayer, the ecosystem. Then I'll give you a tour of Bricklayer's EdTech. And then after that, I'll share some ideas that I'm exploring on how to use Unity to increase engagement. And then I'll conclude the talk by giving some examples showing how Bricklayer can be used to teach computational science. So Bricklayer, the ecosystem, is a set of apps, online tutorials, curriculum, and documentation that teaches mathematical thinking, computational thinking, and coding in an engaging manner using art as the medium. So to date, Bricklayer curriculums have been used across Nebraska, eastern Nebraska, in over 100 schools, and this is across the K-16 spectrum. And at my university, the University of Nebraska-Omaha, there are two classes I'd like to mention. One is Math 1120, and Math 1120 satisfies the Gen Ed math requirement for non-STEM majors. And so what that means is that if you are not a STEM major, this class serves as a substitute or an alternative for college algebra. And at our university, that's a huge thing. And across the United States, this is a huge thing as well. And this class is also taught at our community college, and the credits can be transferred back to our programs. So in the computer science department, where I'm a professor, I use Bricklayer to teach computational science. And this is an introductory courses, so both of these courses assume no background in programming at all. So at the end of the day, Bricklayer programs are written in the functional programming language SML. And what you see here is a lightweight IDE that we've developed for that purpose. And so Bricklayer EdTech then supports the development of the prerequisite skills needed to effectively write Bricklayer programs. So that brings us to a tour of Bricklayer's EdTech. So here, aside from the IDE that I just showed you on the previous slide, this is the EdTech of Bricklayer. And these are all mobile-friendly apps. Somebody says the links are not working. There may be some time on a download, so there's a fluctuating time if you're doing the first two links, and the YouTube links should work. So back to this, we have these mobile-friendly apps. This is a screenshot from my phone, and I want to talk about each of these briefly. So Vitruvia is an interactive web app that focuses on reading code. So you get to see sort of a snippet of code, and the person is asked to recreate the artifact in a grid that would have been created had this code been executed. And these apps, and a number of these that I'm going to be talking about here, I would put in the HyperInteractive category. So you can submit an answer, you get, whether you got it right or wrong, you get instant feedback. You can try again. You can look at the answer in the back of the book. So show solution, and you can do this in any order. So you can do show solution and then submit an answer. And so this kind of hyper interactivity has resulted in some students, not all, but some students having sort of a cavalier approach as to what it takes to understand something fully, a concept, before you move on to the next one. And so to blunt that behavior a little bit, I created a test generator, and actually all of these apps that are of this kind have test generators associated with them. And so a test generator lets you select some subset of concepts, some number of questions, and then in this testing environment, students get instant feedback whether they got it right or wrong, but they can't try again, and they can't consult the answer before they consider their own solution. All right, so where Vitruvia was about reading code, Quill is sort of the flip side of this, and it's about writing code. And so at this stage in coding, Bricklayer programs are flat, so they consist of just sequences of function calls. And so what you do here in this app is through mouse clicks, you create those sequences. So the name of the function here is put2d. You click on the right here, you click on the button that says put2d. You then pass the parameters to that function, so the shape, the color, and then in the grid, you click where you'd like that rectangle to be placed. And as you're doing this incrementally, the corresponding text shows up in the lower left corner. So what you have here, right, you could have created this artifact using 8 function calls, where each function call places a single unit brick of the right color at the right place. However, overwriting is allowed in Bricklayer. And so what you can do here is you can do a 2x2 black brick two of those. And then within those 2x2 bricks, you can place two or overwrite two white bricks along the diagonal. So that gets you to 6 function calls. And so Quill does have Quill type 2 exercise, which I'm not going to cover today. They place constraints on how many function calls you have to build something. And these problems can be actually quite challenging. Don't have time to talk about that, but I do want to talk about Quill type 5 construction exercises. So a rite of passage sort of at this beginning stage of Bricklayer is the creation of pixel art. And so pixel art is more about being organized, being reliable, having good processes in place. And the goal here is you have a picture of some pixel art, you translate that picture into code, into Bricklayer code, and when you execute that Bricklayer code, the execution recreates that image, right? So that's the pixel art challenge. And pixel art can be incredibly complex. And so to be organized about how you create such pixel art, it's really important to kind of give that some thought. And there are two general algorithms that are effective for this in general, right? And one of them is a row major construction algorithm. The other one is a column major construction algorithm. And so, so in a row major construction algorithm, you go from bottom to top, use one row at a time. That's how the pixel art is created. And each row is created from left to right. And so what this Quill exercise, this type 5 exercise will do, it will make sure that you build an artifact according to that algorithm. And it will tell you when you get it wrong. And it will let you undo and back out over a mistake rather than start over. All right, so that then gets you to Bricklayer Lite, which is one step closer to text-based code. This is a block-based programming environment. It's based off Google Blockly. And there are more opportunities for you. You have less guidance, more opportunities to make mistakes. So you have to deal with a little bit more complexity here. You have to put semicolons at the end of these function calls. And any place where you can type in text, like the dimensions of these rectangles or their positions, you have an opportunity to make a mistake. And so this thing here is very verbose and very comprehensive in the kind of feedback that it gives you. So if you build a rectangle that's too big for the space, that exceeds the space that it's placed in, it will tell you this and let you fix it, right? So it treats that as an error. If you forget a semicolon, it will give you visual cue and also some verbal feedback on this stuff. Okay. Now, so that then gets you to this text-based programming. Now, that's the coding side, the mechanics of coding, what you're tracking and stuff. But to build artifacts, especially ones that have patterns and things like this, mathematic, geometric constructs, it's important to understand, it's beneficial to understand properties that artifacts have. And symmetry is an important property. And so this app here, Mystique, focuses on a horizontal and vertical reflection symmetry, as well as twofold and fourfold rotational symmetry. And on this particular problem here, it's a type 1 problem, which means the artifacts fit inside a 3x3 grid, as opposed to a type 2 problem where the artifacts fit in a 5x5 grid. So this one here, imagine a horizontal line cuts the artifact in half, and your goal is to flip this around that horizontal line. So you can talk about algorithms for how you would move one cell at a time and recreate this. So that's one way of doing it. However, the artifact is a familiar shape here. It's the letter H. And the hope is that it's small enough that maybe you can just flip this whole thing in your mind's eye. And so the Mystique artifacts are selected intentionally to encourage that kind of thinking. Now, another kind of exercise that Mystique has that's very popular among the students is called a completion. And what you have here is an artifact on the left. It's actually a fragment. And what you need to do to this artifact is you need to add cells to it, the minimum number of cells, so that the artifact that you have created has, in this case, horizontal, vertical, and twofold symmetry. So that's the goal of a completion. And then there's one last app of this kind, and it's called Links. And Links focuses on understanding sequences in visual terms. And so the idea here, the key insight, right, is that how does a larger artifact how can it be defined in terms of a smaller artifact? So we're talking about inductive constructions and these kind of things, but only in nonverbal and visuals in a visual setting. Okay, so that brings us to the grid. So the grid has been around for a very long time, and it initially started out as graph paper, as virtual graph paper, but since then has had a lot of capabilities added to it. And the one that I want to talk about today is called frames. So the way the grid works is if you click on a cell, then that cell will be filled with whatever the selected color is. So it would take 3 mouse clicks to create this artifact. Now, if you turn on the frame mode, you can take a snapshot of that. So now you have a copy of that entire artifact. And if the frame mode is on, if you now click, you will paste that the entire contents of what you've copied at a certain location. So if I start here, I have 3 mouse clicks to create the first artifact. I then take a snapshot. 2 additional mouse clicks gets me this one. I can take another snapshot. 2 additional mouse clicks gets me this one, and so on. Now, so you can ask students to create something like this, but they may not actually follow this algorithm, this kind of a construction. And so the grid also allows you to see the construction graph that took place. And so this is a composite graph. So it shows the mouse clicks corresponding to each frame. That's sort of these L-shaped mouse clicks that are in different colors. You can view subsets of this graph as well, but I would like to draw your attention to the bottom one, the white graph. That is the unit-based construction that would happen. So this is basically like a trace through the code, right? Now, you could do other algorithms to construct that artifact. So the one on the previous slide was constructed from left to right. And if you constructed it from right to left, you would get this kind of a graph. And this one here is not using frames at all. It's what I would sort of call a top-down construction, where you draw the outline of the largest triangle first, and then you break that down into smaller problems, and then you work on the smaller triangles, and you keep doing that. And then the last one here is what is the graph that results if you construct this using the elementary cellular automata rule 30. Now, originally, Bricklayer was intimately connected with Lego Digital Designer. And so what that meant was that the color of bricks corresponded to whatever the colors of Lego bricks, right? So it was sort of a limitation. And also Lego Digital Designer was the primary display tool, and it was not well suited for this kind of a use. So it would have problems if you had large artifacts with many bricks in them. And so since then, I have built a custom native display tool, a web viewer, and I've also added RGB values as well as the ability to store numbers in these cells, so fixed point numbers. And that has opened up the door to a whole different kind of patterns that you can explore. You now have color gradients. So what you see here are Julia sets, so the Mandelbrot set, the original Julia set, and then one of the relatives on the right here. All right, so that pretty much concludes the tour of Bricklayer's EdTech. Now I'd want to share with you some ideas that I've been exploring with Unity. And I know it seemed like some people, I'm kind of just looking a little bit at the comments, the feed, but it seemed like people are having some problems with some of the links that I'm providing. So this is a YouTube video. You should be able to get to this. And what you see here is some ideas that I'm exploring on how to use Unity, a Unity game, as a display tool for Bricklayer artifacts. So right now, you run a Bricklayer program, you have a show function. That show function triggers the web viewer that lets you see the artifact. There's a show Unity function that I'm working on that will put you into a game like this. And in this game, you could have some Bricklayer EdTech, there's a Mystique puzzle there that may be part of gameplay. And at the bottom, what you see is through a spell, the person is recreating their artifact. So this is the artifact that their code, that their SML program produced. It's just showing up in this Unity game, and you can now blow it up and build it again and all that kind of stuff. So here's links to 2 art galleries that, again, it does work, but I have heard from people that sometimes the download takes a little bit, the time. but that's very fluctuation. It fluctuates a lot too. All right, so in this first link here gets you to an art gallery where what you see here on the wall, all of that art was created by students. And these are sort of, at least what you see here is sort of in the masterpiece category, in the sense that most students don't put this kind of work into the creation of pixel art. What you can do, though, in this gallery is you can run around and rate each one of the paintings by selecting the appropriate rating below, right? These are these circles. And then on the top, if you press R on your keyboard, it takes you to a rating summary page, and you get to see all the ratings associated with all the paintings sort of in a two-dimensional format. So anyway, I encourage you to go walk in there. If you have difficulty, you can always send me an email afterwards and we can try to figure something out. I did another one of these kind of galleries here to show what's possible art-wise with respect to mathematical art. So what you see here are fractals, space-filling curves. There's some cardioids in the back there, complete bipartite graphs, those kind of things. And there's some really cool stuff on this side. And so I would encourage you to go in there and check it out. That's my sales pitch there. And if you want to send me a rating summary, that would be cool. So that gets me then to a different kind of an engagement. And this is the game called the Kessel Run. And what I'm doing here in these Unity games is I'm pulling in directly web pages. So this is not what you see here where it says Concept 1, Exercise 9. That is not programmed in Unity. That's just a URL to a web page. And these are these Bricklayer apps, right? This EdTech. And what you can do here is you solve this puzzle. And on the other platform, there's another puzzle. You jump over, you solve that one, you keep going. And so if you watch the video, so I have a YouTube video that shows this, stick around for this award ceremony at the end. It's gotten a lot of good reviews. All right, so that brings me to the last part of the talk. And this is about how to use Bricklayer to teach computational science. So the fact that we have RGB values, right, that lets us do color gradients, and that we have fixed point numbers lets us do mathematical computations of these kind of structures where we can store that kind of information in them. It opens up the door to modeling, to using Bricklayer to model a bunch of cellular automata-based stuff. And so there's some books here that give you good examples to draw from, and I want to talk about a couple of these kinds of examples. So this first one here is Percolation Theory. And in Percolation Theory, you have a square that represents a material, and the material in that square has a certain density. So in this case, a black cell represents material present in this square, and an empty cell represents no material present. So you have a material of a certain density, you pour water on the top, and if the water flows all the way down to the bottom, the material percolates, and not, it doesn't. And so some interesting things about percolation theory, right? One is there's this number called a percolation threshold, such that for large enough squares, if the density of the material is below that threshold, it always percolates pretty much. And if it's a little bit above that threshold, it never percolates. And furthermore, that threshold, how to calculate that is an open question in math. And so you actually have to calculate these things through simulation. So I have this Bricklayer library that lets you run batch tests and summarize them and do all kinds of things. And so students can then get these numbers, plug them into an Excel spreadsheet and create this kind of a graph. So this is a sigmoid function here. And so you can use this for other stuff. So sigmoid also represents how a pandemic goes through a population. It's that same kind of a function. And so people have, and I have also, played around with that a little bit in the context of a percolation. So here what we have is the white cells here represent that segment of the population that is wearing masks, and the blue cells are those people that are not wearing masks. And so in the center of this square then, we plunk somebody down that has COVID, and then there's some rules governing the transmission of COVID and outcomes and so on. And so the black cells here mean you caught COVID. The red cell means you had COVID, but you don't have it anymore because you're dead. And the yellow cell, which is a little bit hard to see, is you have COVID and you're in the hospital. So you can just plug in sort of whatever the current science is telling you, right, as to what the hospitalization rates are and infection rates and death rates and all that, and you can kind of see what happens. Now, the interesting thing about this percolation threshold, right, is if you have a slight change in the percentage of people that are wearing masks, you can have a radically different outcome as far as transmissibility goes. You can do attractor inhibitor systems. So these are Turing patterns here. In the interest of staying on time, I'll just kind of skip over this one quickly, and I'll get to the last one here. So this is thermal imaging, right? And so it's a heat diffusion simulation. This is a camera that I have. I bought it. It's a thermal imaging camera. It cost like $400. And then I have a bamboo cutting board on the bottom and a brass cube. So I heated up the brass cube, let it sit on the cutting board for a couple of minutes, took it off, and then took a picture with the thermal imaging camera. And what you see on the upper right here is that image. So you get temperature ranges, right? What the ambient temperature is, what the hot spot is, and so on. And you can plug those into this heat diffusion simulator, right? And you can run simulations in Bricklayer. And what you see on the bottom here is one of those simulations. And so I think that is all I wanted to talk about today. Thank you very much for attending my talk. Any questions, comments, anything? I guess I go to the Q&A part now. I'll stop my sharing maybe.
Yeah, if you have a question, raise your hand and we can get you live here. So Peter can get you in this time.
Yes.
And the other speaker, the other question too.
Oh, so should I just kind of start answering some of these? So one question was, how long does it take for a student to get from start to something like drawing a fractal? And so the idea here, right? So that the fractal, if you want to talk about frames, like that frame-based construction of a fractal, that doesn't take too long. And I've done this across K-12. So I haven't taught elementary school kids to do fractals like this, but I have taught this gen ed math class. I've taught the computational science class. I've helped people in high schools and stuff. So the goal is to have it be a very smooth, gentle learning curve. Now if people have good background, right, they can go through this much faster, right? So this is the and the inductive stuff. Let's see.
Here, Victor Peter's here, so let's let him jump in and ask.
Oh yeah, okay, yeah, go ahead.
Well, it's a good sign that you're eager to answer all the questions. So I really like this ecosystem that you've developed, and I was just wondering, from a functional programming teacher's point of view, what you can get out of that. So, for instance, what you showed with this repeating structure, basically this fractal-like structure.
Right.
Well, clearly that's a very good hook for students to learn about recursion, right? So I was just wondering, do you have some kind of educational plan for that or experience that you would like to share?
Yeah, so the thing is, on one thing that students can get their head around, it is still a big step, and remember these are novices, is step one is using functions that have been provided to you, understanding how to use those, right? Then the next step is creating your own function, right? And that's a big step, but an even bigger step is creating another function that uses a function that you previously created. So that is a huge sort of a threshold concept, I would say. And so what this inductive stuff, what you works on first is you focus on creating programs, the textual part, how do you create function declarations and such, and then and frames provide you this sort of an outline for how to do this, right? So first you can click these 3 mouse clicks and you can say, I make that a function. We'll call that frame 0. And then frame 1 calls frame 0. And then, so one of the things, so in that sense, you get an inductive construction. It's sort of pseudo recursive, right? You're not actually doing recursion, but as you start playing around with the code, you can parameterize various kinds of things. So one of the things that's really nice with functional programming in general, right, is that it lends itself to transformation. And so you can manipulate stuff, and we can say like, okay, we're going to pull this, we're going to start playing with this code by restructuring it. We're going to parameterize certain things, and we're going to make these variables now, and so on. And so you can gently go from there to a recursive version, right? So you go to a pseudo recursive version, and then you can parameterize that on the subscript, frame 0, frame 1. So if you just, then you're done, right? So so the idea is to gently approach it that way, but it really does matter. So for us in the United States, a lot of time in sort of your standard state schools, right? Recursion is a heavy lift for students, and they generally have not as strong a background as they might in other places. So I think in Europe, they generally have a stronger math background. So which means that they can process the abstractions that come with symbols a lot easier, right? So this is the thing that I've noticed with what math brings to the table, right? In why do you need a certain math background? It's the ability to process symbols like this. Now, Bricklayer has traversals. So that's a way of sidestepping recursion, right? So if you say, I want to traverse space, and for every coordinate you see, you add the two coordinates together. If they're even, it's white. If it's odd, it's black. So you get a checkerboard this way. So there's a lot of really cool things you can explore that way. Let me see if I can, if there's any other, does Bricklayer support graphical composition? So I'm not familiar with that functional geometry, but I will look at this. The goal for Bricklayer was supposed to be not a graphics tool, but sort of a tool that has enough primitives that, hey, since SML is a fully general purpose functional programming language, you can build all the other stuff that you want, right? And so who does that building, whether it's a Bricklayer library or an instructor or the student themselves, right? So that's what gives it some wiggle room as to who you want to target, which audience you want to target with this kind of stuff.
Yeah, so the reason I'm asking is because a lot of the things that you presented, the ideas, are basically transformations of things that you have already built.
Yeah.
In juxtaposition, enlarge them, mirror them, whatever.
Right. Yeah.
So that's why.
Yes, so I will, definitely.
We've gone long already, but let's try to fit in one more question. There was one, how much would a student spend writing actual SML? That's from Xiangji.
So they start, so we start it depends on the audience, but you start very quickly. So if you count Bricklayer Lite as being SML programming, it's the right syntax and stuff, but it's, again, you have some training wheels on there in some sense. They start very, very quickly, right? In that sense, that you can do very quickly. And then when you get to the actual text part, there is a hesitancy. There are, especially if you're not a technical student, there's this big, I'm afraid to start typing, even if it's the same kind of stuff, right? And I even just the other day, a student said, oh, that seemed like so much more complex to type this. And it's like, well, but it's because you can make more errors, right? And so it is, but yeah, so you can get into it fairly quickly. And again, it depends a little bit on the background of the audience. When we work with elementary school kids, they have to be able to type, right, with all 10 fingers. Because if you do this dinosaur typing stuff, then too much cognitive load for that.
I got a long way as a dinosaur, but
yeah.
All right. Well, thank you, Victor. That was a great talk.
Thank you.